Okay, so as we have started resolution topic, so last time in last lecture we have seen resolution by mechanical means. Okay, so there are different resolution methods we have seen. So in that one we have seen different methods. So first one, crystallization method. So that one is the mechanical method of separation of the enantiomers. That one is invented by Louis Pasteur in 1848. Okay, so remaining process of resolutions, they are like through formation of diastereomers. Second method, third third method, we can do resolution by chromatography. Fourth method, through equilibrium asymmetric transformation. Fifth one, through kinetic asymmetric transformation. And one more by biochemical transformation. So, as we have finished by crystallization method of resolution, today we will start the second method, the formation of diastereomers. Okay, so which is very important method of the separation. Okay, so these things we have seen that first mechanical separation of resolution we have seen, that one is invented by Louis Pasteur. But this method has a lot of disadvantages. So this method we cannot apply for various resoluting racemates or other racemates or such types of compounds. So, due to these limitations or drawbacks of this mechanical separation, different scientists, they have developed the different methods. So, out of that one, second method is chemical resolution method, which is based on the formation of diastereomers. Okay, so first method we have seen mechanical separation. Second one is chemical resolution method via formation of diastereomers. Third method is biochemical. This is superficial distribution of these different methods of resolution. Third, third process we can categorize under the biochemical method of resolution, in which biochemical methods we do use the different microorganisms and their enzymatic systems to separate the enantiomers. Okay, so and last one, adsorption method, which comes under the or which include the particularly chromatographic techniques. Okay, so this is the just for broad classification of four different techniques for resolution of the racemic modification. So out of that one, now we will go for the resolution by formation of diastereomers, that is chemical method of resolution. Okay, so why we go for diastereomers? Okay, so why we use the name diastereomers? As we know, enantiomers have identical physical as well as chemical properties. Okay, but diastereomers have different and somewhat different, okay, somewhat different physical as well as chemical properties. Okay, so scientists use this point or this advantage of diastereomers, that they do have different physical as well as chemical properties, and they need use for the resolution. So two enantiomers have the same physical properties. That's why they cannot be separated easily by standard laboratory techniques. Okay, this is one of the these diastereomers, they are beneficial. Okay, so in contrast to enantiomers, two diastereomers have different physical properties, and due to these different physical properties, we can these diastereomers can often be separated via standard laboratory techniques. Okay, so this is the advantage of diastereomers. So now, how to go for this separation? So what we can do, an additional chiral center can be incorporated into a pair of enantiomer, so they can become diastereomers. Okay, so how to go for the separation? So simply we can convert, okay, enantiomers. Okay, so we can convert enantiomers two diastereomers. Okay, so enantiomers have identical physical properties such as solubility, melting point, resolution is extremely difficult. Okay, so why enantiomers, separation of enantiomer is difficult? Because they have identical physical properties. That means R enantiomer and S enantiomer. If we will consider these two enantiomers, these two enantiomers have identical physical as well as physical properties like solubility, melting point. So as R enantiomer and S enantiomer, if they do match their melting point and boiling point or other melting or other properties, physical properties, so how we cannot, it's getting very difficult to separate them. But diastereomers on the other hand have different physical properties, and these, that means they do have maybe separate melting point. Okay, R diastereomer and S diastereomer, maybe they do have different physical properties like different melting point or boiling point. Okay, at least slightly difference should be there in diastereomers. And these important the difference, or this small difference also we can may use to separate from each other. R diastereomer and S diastereomer we can separate from the each other. So reaction of racemids. Okay, so here is the a little bit diagrammatic presentation of how we can go for the resolution. Okay, so first we can take enantiomers. Okay, racemic mixture here I have shown in the picture. Racemic mixture we can see first R plus S enantiomer. Okay, we can say enantiomer. Here I have written enantiomer. Okay, this is racemate, both R and S are present. So how to do that one? So to separate them, what we can do, we can use any chiral reagent. Okay, so to separate them from each other, we can use any type of resolving agent, we can say. Okay, so this one here is chiral reagent they have used. This one is nothing but the resolving agent. Okay, so what kind of resolving agent we will see on next slide, but first pay attention that yeah, we can expose our R plus S enantiomer or racemic mixture with one resolving agent. It should be chiral resolving agent, and chiral means we have to use only one form, either R form of chiral resolving agent or S form of the chiral resolving agent. So pay attention what is happening. If we will add racemate plus chiral reagent, so what this chiral reagent that one is doing, that chiral reagent is getting react or get form complex with these enantiomers, R plus S enantiomer complex. Okay, there is a formation of complex in between this chiral resolving agent and this enantiomer. So what type of complex they do form? Here intermediate species are nothing but the complex. So here pay attention, chiral reagent we have only one isomer, either R or S. So this R and S they do complex with this R and S enantiomer. Okay, so here we got R enantiomer. Okay, R complex, and as well as this chiral R reagent complex with S enantiomer of the racemic. Okay, so here we got R diastereomeric complex and RS diastereomeric complex. So here by the mean of chiral reagent, chiral resolving agent, we have successful by complexing with chiral resolving agent, we are successful to separate this enantiomer R and S here. Okay, so here in this intermediate only your racemic mixture R and S got separated into these two different complexes, two different diastereoisomers. Okay, so like that here we got our complexing reagent. Now again on treatment, on further treatment, we can separate now this R. Okay, R from this one with blue color I have indicated R from this racemic mixture, and S I have indicated from this racemic mixture. So here we can separate R enantiomer and S enantiomer. Okay, so this is the only the general idea for the separation of the our chiral racemic mixture, not chiral racemic mixture with the help of chiral resolving agent.